10 billion light-years away, a black hole weighs 66 billion times more than our star. Its event horizon stretches 40 billion miles across. That means our entire solar system, from Mercury to Neptune, could fit inside the point of no return. This is TON 618, the most massive black hole ever discovered. You will witness how it bends time itself, how it shines brighter than 400 trillion stars combined, and why it should not exist according to everything we know about the universe. If you are ready to explore the impossible, hit that like button and subscribe. Prepare yourselves. We begin. In 1957, a French astronomer named Marie-Hélène Ulrich pointed a telescope at a faint smudge of light in the constellation Canes Venatici. She marked it down as object number 618 in the Tonnant-Zintler Observatory catalogue, TON 618. Nothing about it seemed remarkable at first, just another dim point among billions. She had no idea she was looking at the most massive single object ever found in the universe. For decades, TON 618 sat in astronomical records, ignored and unremarkable. Astronomers assumed it was a distant star or maybe a small galaxy. The technology to measure its true nature did not exist yet. Spectrographs could barely capture its light. Distance calculations remained guesswork, but that faint glow was hiding something monstrous. By the 1970s, better instruments started revealing secrets. Scientists measured the light signature coming from TON 618. The spectrum showed extreme redshift, meaning this object was racing away from us at tremendous speed. More importantly, it meant TON 618 was not nearby. It was not even close. The light we see today left that object when the universe was less than 3 billion years old. We are looking back in time, witnessing something from the cosmic dawn. Then came the real shock. Astronomers measured how much energy TON 618 pumped into space. The numbers made no sense. This tiny dot in the sky was producing more light than entire galaxy clusters. Something 10 billion light-years away should barely register on our instruments. Yet TON 618 blazed with the fury of 400 trillion stars packed into a region smaller than our solar system. Only one explanation fit the data: a supermassive black hole, actively feeding, surrounded by a swirling disk of superheated matter. But when scientists calculated the mass needed to produce that much light, the numbers broke every model. 66 billion times the mass of our star, concentrated in a single point. Most black holes in galaxy centers measure millions or maybe a few billion solar masses. TON 618 crushed those records. It weighed more than some entire galaxies, and it existed when the universe was young, barely formed. Standard cosmology could not explain how something this massive appeared so early. There had not been enough time for it to grow by consuming stars and gas. The discovery triggered arguments across astronomy departments worldwide. Some scientists rejected the measurements outright. Others proposed wild theories involving direct collapse from primordial gas clouds or massive mergers of smaller black holes in the early universe. Every explanation required bending the rules of physics. Confirmation came from multiple observatories using different methods. Radio telescopes detected intense emissions. X-ray satellites picked up the signature of matter being torn apart and superheated. Optical telescopes measured the Doppler shifts of gas clouds orbiting something invisible and impossibly heavy. Every instrument agreed. TON 618 was real, and it was enormous. Today, we know TON 618 sits at the heart of a distant galaxy we can barely see. The black hole itself remains invisible, as all black holes are. We detect it only by what it does to everything around it. Matter spirals inward, accelerates to near light speed, heats to billions of degrees, and screams radiation across the electromagnetic spectrum before crossing the event horizon and vanishing forever. Understanding TON 618 changed how we think about black hole formation. It revealed that the early universe was far more violent and chaotic than models predicted. Massive structures formed faster than they should have. The rules we thought governed cosmic evolution needed rewriting, but the discovery was just the beginning. Measuring its mass was one thing. Comprehending its true scale would prove far more disturbing. Because when you calculate the size of TON 618's event horizon, you realize we are dealing with something that challenges human imagination. Calculating the mass of a black hole 10 billion light-years away sounds impossible. You cannot see it. You cannot touch it. You cannot send a probe there. Yet astronomers did it, and when the first calculations came back, teams threw out their results and started over. The numbers were too big. Something had to be wrong. The method relies on how bright a quasar shines. When matter falls toward a black hole, it does not drop straight in. Gravity and angular momentum force it into a spinning disk called an accretion disk. Friction between particles in this disk heats the material to extraordinary temperatures. The inner edge of the disk reaches millions of degrees. That heat produces light. The brighter the quasar, the more matter is falling in. The more matter falling in, the stronger the gravity must be. The stronger the gravity, the more massive the black hole. Scientists can work backward from brightness to mass using well-established physics. The math is solid. The problem was that the math kept saying TON 618 weighed 66 billion solar masses. Early teams assumed their instruments malfunctioned. They recalibrated everything and measured again. Same result. They checked for gravitational lensing effects, wondering if another massive object between us and TON 618 was magnifying its light artificially. No lensing detected. They considered whether multiple black holes might be clustered together, creating a combined signal. The light signature showed a single source. One astronomer proposed that TON 618 might be consuming an entire galaxy worth of material all at once, temporarily boosting its brightness beyond normal levels. But the quasar had been stable for decades of observations. Whatever was happening, there was not a temporary flare. This was its standard output. The resistance to accepting the measurement came from a fundamental problem in cosmology. Black holes grow by eating. They consume gas, dust, and stars. Each meal adds mass. But there are limits to how fast a black hole can feed. This limit is called the Eddington limit. When matter falls toward a black hole, it gets compressed and heated. That heating produces radiation pressure pushing outward. Eventually, the outward pressure from radiation equals the inward pull of gravity. Matter cannot fall in any faster. The black hole has reached its maximum feeding rate. This creates a speed limit on black hole growth. Scientists calculated how big a black hole could grow in the first 3 billion years of the universe, starting from a stellar mass black hole and feeding at the Eddington limit continuously. The answer came out to roughly 1 billion solar masses. Maybe 10 billion if you pushed assumptions to their breaking point. TON 618 weighed 66 billion solar masses. It should not exist. The universe had not been around long enough for it to grow that large through normal feeding. Some researchers proposed that TON 618 started much bigger. Instead of forming from a single massive star, maybe it collapsed directly from a primordial gas cloud. But even direct collapse models struggled to produce seeds heavy enough. Others suggested TON 618 was the product of countless black hole mergers in a dense star cluster. That could work, but it required a series of unlikely events happening in perfect sequence. The most uncomfortable possibility was that our understanding of early universe conditions was incomplete. Maybe matter was distributed differently than we thought. Maybe feeding rates could exceed the Eddington limit under exotic conditions we had not yet discovered. Maybe the laws of physics operated slightly differently when the universe was young and dense and hot. Every explanation had problems, but the measurements remained consistent. Multiple independent teams using different telescopes and methods all arrived at the same conclusion. TON 618 was real, it was massive, and it was old. The implications stretched beyond one unusual object. If TON 618 could form in the early universe, other supermassive black holes might be hiding in distant quasars, equally impossible and equally real. Our timeline of cosmic structure formation might need complete revision, yet, even knowing its mass, most people still could not grasp what 66 billion solar masses actually meant. Numbers that large become abstract. To understand the true horror of TON 618, you need to see it in human terms. Imagine standing on Earth and looking up at our star. That ball of fusion in the sky measures 864,000 miles across. Light takes 8 minutes to reach us from its surface. Now, multiply that star by 66 billion. That is the mass compressed into the singularity at the heart of TON 618. But mass alone does not capture the scale. Black holes concentrate their mass into impossibly small points. The real measure of a black hole's size is its event horizon, the boundary where escape becomes impossible. For TON 618, that boundary sits 40 billion miles from the center. Our entire solar system, from the innermost planet Mercury out to the frozen orbit of Neptune, spans about 5,600,000,000 miles. Neptune circles at roughly 2,795,000,000 miles from our star. The event horizon of TON 618 stretches 14 times farther than Neptune's orbit. Picture this. You could place our star at the center, where TON 618 singularity hides. Mercury, Venus, Earth, and Mars would sit deep inside the event horizon, long since consumed. Jupiter would be inside. Saturn would be inside. Uranus would be inside. Neptune would be inside. You could fit 14 copies of Neptune's orbit inside the point of no return. Voyager 1, the most distant human-made object, has been traveling away from our star since 1977. It currently sits about 14,700,000,000 miles away, well into interstellar space, beyond our solar system. If TON 618 replaced our star, Voyager 1 would still be inside the event horizon, falling toward oblivion with no hope of escape. The scale becomes even more disturbing when you consider density. Our star is big, but relatively empty. Its average density is similar to water. You could theoretically swim through parts of it if you could survive the heat. TON 618's event horizon encloses a volume millions of times larger, yet all its mass crushes down to a point smaller than an atom at the center. This creates gravity gradients so extreme they defy intuition. At the event horizon itself, gravity is strong enough to trap light, move inward even slightly, and the pull intensifies. Move outward, and space begins to curve less severely. But the distance over which this happens is cosmic. You could travel millions of miles and still measure significant changes in gravitational strength. Comparing TON 618 to the black hole at our galaxy's center makes the contrast even sharper. Sagittarius A star, the supermassive black hole we orbit, weighs about 4 million solar masses. Its event horizon measures roughly 17 million miles across. You could fit the entire thing comfortably inside Mercury's orbit. TON 618 weighs 16,500 times more than Sagittarius A star. If you placed both black holes side by side, Sagittarius A star would look like a marble next to a house. We orbit a marble. TON 618 is the house. Think about what that means for any civilization unlucky enough to live near TON 618. Their entire concept of space would be warped by this object. Gravitational effects would dominate their astronomy. Time would flow differently depending on where you measured it. The tidal forces alone would tear apart anything that ventured too close. Our solar system feels safe because our star is stable and predictable. We orbit at comfortable distances where gravity is strong enough to hold us in place, but weak enough to allow stable orbits. Near TON 618, there is no comfortable distance. The zone where planets could exist stretches across light years, And even there, the black hole's influence would be inescapable. Visualizing 40 billion miles is nearly impossible. Human brains did not evolve to comprehend distances that vast, but understanding the scale matters because it reveals something profound about the universe. Objects this large should not exist, yet they do. And TON 618 is not just big, it is massive enough to warp the very fabric of space and time around it in ways that challenge physics itself. Which brings us to the edge, the event horizon, the point where reality breaks down. The event horizon is not a physical surface. You cannot touch it. You cannot see it. It is simply the distance from a black hole where the escape velocity equals the speed of light. Cross that invisible line, and the universe forbids your return. For TON 618, that line sits 40 billion miles from the singularity. Light moves at 186,000 miles per second. Nothing in the universe travels faster. This creates the ultimate speed limit. When gravity becomes strong enough to pull light backward, no force in physics can overcome it. Rocket engines would not help. Matter cannot accelerate to light speed. Once you cross the event horizon, every direction in space points inward. Even moving away from the black hole still brings you closer to the singularity. The size of an event horizon depends entirely on mass. More mass means stronger gravity means a larger forbidden zone. The formula is simple. Take the mass, multiply by the gravitational constant, multiply by 2, then divide by the speed of light squared. For TON 618, that calculation produces a radius of 40 billion miles. At that distance, space curves so severely that it folds back on itself. Imagine a slope that gets steeper and steeper until it becomes vertical, then tilts past vertical and curves completely over. That is what space-time does at the event horizon. The geometry becomes so warped that all paths lead down. Standing at the event horizon of TON 618 would feel deceptively normal, at least initially. Gravity at that distance, despite being strong enough to trap light, would not crush you instantly. The black hole is so massive and the event horizon so large that tidal forces spread out over huge distances. You could cross the boundary without even realizing it had happened. This is radically different from smaller black holes. A stellar mass black hole, formed from a collapsed star, might have an event horizon only a few miles across. The tidal forces there would rip you apart before you even got close. TON 618's immense size creates a gentler gradient. You would have time to contemplate your fate. But make no mistake, once across that line, your fate is sealed. Physics offers no loopholes. You cannot quantum tunnel your way out. You cannot use wormholes. You cannot reverse time. The event horizon is absolute. It is the universe saying no. What happens to matter that crosses depends on perspective. From the outside, someone watching you fall would see something strange. As you approach the event horizon, you would appear to slow down. Your movements would become sluggish. Colors would redshift toward darkness. Eventually, you would seem to freeze at the boundary, hovering there forever while the image faded to black. This is not an optical illusion. Time dilation near the event horizon is real. From your perspective, you fall through normally. But from the perspective of someone far away, time for you has slowed to a crawl. The photons carrying your image take longer and longer to escape the gravity well. Eventually, they redshift beyond detection. You vanish. From your perspective, the experience would be different but equally bizarre. You would fall through the event horizon in finite time, maybe seconds, maybe minutes, depending on your trajectory. The universe outside would appear to speed up. Stars would age rapidly. Galaxies would spin. Billions of years of cosmic history would flash past before your eyes. Then you would cross over, and everything would change. The singularity would no longer be a point in space ahead of you. It would become a moment in your future, as inevitable as next Tuesday. No matter which direction you accelerated, you would move closer to it in time rather than space. The event horizon of TON 618 encompasses a volume of space larger than most star systems. Inside that volume, the normal rules of spacetime cease to function. Cause and effect become tangled. Directions lose meaning. The universe inside an event horizon is fundamentally alien. And beyond that boundary, something even stranger waits. The point where all the mass hides. The singularity. The place where physics admits defeat. Time is not constant. It flows at different rates, depending on how strong gravity is around you. This is not philosophy. This is measured fact. Atomic clocks on satellites tick faster than identical clocks on Earth's surface. The difference is tiny, billionths of a second per day, but real enough that GPS systems must account for it, or they would give wrong directions. Near TON 618, time dilation stops being a technicality and becomes overwhelming. A clock sitting just outside the event horizon would tick dramatically slower than a clock far away in deep space. The closer you get, the more severe the effect becomes. At the event horizon itself, time dilation approaches infinity. Einstein's general relativity explains why. Mass curves space-time. The more mass, the more curvature. Time is part of that geometry. When space bends, time bends with it. Gravity does not just pull objects together, it literally stretches the flow of time. Imagine two observers with synchronized watches. One stays far from TON 618, safely in flat space-time. The other descends toward the black hole on a rocket, stopping at various distances to measure time dilation. At 1 billion miles out, the difference would be noticeable but small, a few seconds per hour. At 100 million miles, the gap widens, minutes per hour. As the descending observer approaches 40 billion miles, the event horizon boundary, the effect explodes. Every second that passes for them corresponds to thousands of seconds for the distant observer. Then millions, then billions. Time essentially stops. From the perspective of the person falling in, nothing seems wrong. Their watch ticks normally. Their heartbeat feels regular. But if they could look back at the universe they left behind, they would see it speeding up like fast-forward video. Stars would live and die. Galaxies would evolve. The cosmos would age before their eyes. This creates a paradox for any civilization trying to study TON 618 up close. Send a probe to the event horizon, and you could wait millions of years for data to return. What feels like a few hours to the probe is epochs of time for everyone else. Long-duration missions become impossible. Even brief observations take longer than civilizations survive. The time dilation also affects how we see the accretion disk. Matter spiraling toward the black hole experiences different rates of time depending on distance. The inner edge of the disk, closest to the event horizon, moves through time much slower than the outer edge. This creates strange visual effects. Light from the inner disk gets redshifted and stretched. The disk appears warped and distorted. Gravity also bends light paths. Photons traveling near TON 618 follow curved trajectories through warped space. This means you can see multiple images of the same object. Light from a star behind the black hole might curve around both sides and reach your eyes from two different directions. You see the star twice. Close enough to the event horizon, light can orbit the black hole in circles. This creates a region called the photon sphere. Any light entering this zone either falls in or escapes, but some photons circle the black hole multiple times before choosing a fate. You could theoretically see the back of your own head if you positioned yourself correctly. Time dilation near TON 618 reveals something profound about black holes. They are not just objects sitting in space. They are regions where space and time become so deformed that the concepts lose meaning. The event horizon is not just a boundary in space. It is a boundary in time, separating the universe we know from something fundamentally different. And here is the disturbing part. Every black hole does this. Stellar mass black holes, supermassive black holes, all of them warp time. But TON 618 does it on a scale that affects volumes of space larger than solar systems. The distortion extends across billions of miles. You would feel the effects long before you saw the event horizon. This makes TON 618 not just the most massive black hole, but the largest time machine in the known universe. It creates temporal gradients so steep that moving a few million miles closer or farther changes how fast you age. And at its heart, where the singularity waits, time may not exist at all. But the black hole itself is dark and invisible. What makes TON 618 visible from 10 billion light-years away is what surrounds it, the accretion disk, the spiral of doomed matter. The black hole itself emits no light. Light cannot escape. What we see when we look at TON 618 is the matter dying as it falls toward oblivion. That dying matter shines brighter than 400 trillion stars. An accretion disk forms because infalling matter has angular momentum. Objects falling toward a gravitational center do not drop straight down. They spiral. The spiral flattens into a disk due to collisions between particles. Everything settles into the same plane, rotating in the same direction, forming a structure that looks like a cosmic hurricane. For TON 618, this disk is enormous. It stretches across light-years of space. Gas and dust and shredded stars swirl inward at velocities approaching the speed of light. The inner edge hovers just beyond the event horizon, the point of no return. The outer edge extends far enough that planets could orbit within it if any survived. Friction generates heat. As particles in the disk collide and rub against each other, they transfer energy. Temperature rises. The inner regions of the disk, moving fastest and experiencing the most friction, heat to billions of degrees. Matter at these temperatures does not just glow, it screams radiation across the entire electromagnetic spectrum. The disk emits X-rays, ultraviolet light, visible light, infrared, and radio waves simultaneously. If you could see it with human eyes, it would appear as a blindingly bright ring around an invisible center. The color would shift depending on distance. The outermost regions might glow dull red, moving inward, orange, yellow, white, then blue, so intense it would burn retinas. But the disk does not just emit light, it emits more light than should be physically possible from such a small region. The luminosity of TON 618's accretion disk reaches 400 trillion times the output of our star. Pack all the light from every star in the Milky Way together, and TON 618 outshines it by a factor of thousands. This extreme brightness makes TON 618 a quasar. Quasars are the brightest sustained objects in the universe. They represent supermassive black holes actively feeding on massive amounts of material. The term quasar comes from quasi-stellar radio source, because early astronomers thought they were strange stars. Only later did we realize they were black holes billions of light-years away, so bright we could see them across cosmic distances. The amount of matter TON 618 consumes to maintain this brightness is staggering. Calculations suggest it eats roughly 10 solar masses of material every year. That is 10 stars worth of gas and dust spiraling past the event horizon annually. Over millions of years, that adds up to billions of solar masses consumed. Yet the accretion disk is not uniform. It has structure. Hotspots form where density increases. Magnetic fields thread through the plasma, creating loops and filaments. Turbulence causes fluctuations in brightness. Sometimes TON 618 flares brighter. Sometimes it dims slightly. These variations happen over timescales of months or years, fast enough that we can observe changes within human lifetimes. The disk also serves as a cosmic particle accelerator. Magnetic fields in the superheated plasma trap charged particles and whip them to near light speed. These particles spiral along field lines, emitting synchrotron radiation. The energy involved is absurd. Individual electrons carry energies higher than anything we can produce in our most powerful particle accelerators on Earth. Temperatures in the inner accretion disk reach billions of degrees Kelvin. For comparison, the core of our star sits at around 15 million degrees. The surface of our star measures 6,000 degrees. Matter in TON 618's accretion disk is hundreds of thousands of times hotter than the surface of our star, and hundreds of times hotter than our star's core. Nothing solid can exist at these temperatures. Atoms break apart into plasma. Electrons strip away from nuclei. Matter becomes a soup of charged particles moving at relativistic speeds. The disk is not a solid structure. It is a maelstrom of ionized gas, held together only by gravity and magnetic fields. And from this chaos, jets emerge. Massive fountains of matter and energy that shoot outward from the poles of the black hole, perpendicular to the accretion disk, reaching speeds that approach the ultimate cosmic limit. 400 trillion is an incomprehensible number. If you counted one star per second without stopping, it would take 12 million years to reach 400 trillion. That is how many stars worth of light TON 618 produces from a region smaller than our solar system. The Milky Way contains roughly 200 billion stars. TON 618 shines 2,000 times brighter than our entire galaxy. Andromeda, our nearest major galactic neighbor, contains about 1 trillion stars. TON 618 outshines Andromeda by a factor of 400. Even galaxy clusters, containing hundreds of galaxies with trillions of stars combined, can be dimmer than this single object. This brightness is not metaphorical. It is measurable, quantifiable energy output. Astronomers calculate luminosity by measuring the flux of light reaching Earth and accounting for distance. TON 618 sits 10 billion light-years away, so far that its light has been traveling toward us since the universe was less than 3 billion years old, yet we can still detect it with ground-based telescopes. The light we receive is faint only because of distance. If you could place TON 618 at the same distance as Andromeda, roughly 2.5 million light-years away, it would dominate the night sky. You could not look directly at it. The glare would be painful. It would cast shadows on Earth at night. Our entire sky would be bathed in its radiation. The energy output comes from mass conversion. When matter falls into a black hole, it does not just disappear. Some of its rest mass converts to energy, according to Einstein's equation. The efficiency is shocking. Nuclear fusion, the process that powers stars, converts about 0.7% of mass into energy. Accretion onto a black hole can convert up to 40% of mass into energy before it crosses the event horizon. This means TON 618 is the most efficient engine in the known universe. Every kilogram of matter that spirals into the accretion disk releases more energy than 4,000 kilograms of matter undergoing fusion in a star. The black hole extracts energy from gravity itself, tapping into the warped space-time around the event horizon. The brightness also reveals something about the feeding rate. To sustain 400 trillion solar luminosities, TON 618 must consume roughly 10 solar masses of material per year. That is equivalent to 10 stars worth of gas and dust crossing the event horizon annually. Over 1 million years, that is 10 million solar masses consumed. Over 1 billion years, 10 billion solar masses. But there is a problem. TON 618 weighs 66 billion solar masses. If it has been feeding at this rate since the early universe, the math does not add up. It should be even more massive than it is. This suggests TON 618 has not been feeding continuously. Quasars are not eternal. They turn on and off as fuel supplies fluctuate. The brightness we see today represents a snapshot of TON 618 during an active feeding phase. There may have been periods when the accretion disk thinned or disappeared entirely. The black hole would still exist, but it would be dark and undetectable. We only see TON 618 because it happens to be feeding right now, or rather, it was feeding 10 billion years ago when the light we see today began its journey. This raises an unsettling question. How many dark, supermassive black holes are lurking in the universe, invisible because they are not currently consuming matter? TON 618 might not be unique. It might simply be one of the few we can see because it is active. Countless others could be hiding, waiting for fresh fuel to ignite them back into visibility. The sheer output of TON 618 also affects its surroundings. The radiation pressure from the accretion disk is strong enough to push gas and dust away. This creates a feedback effect. The more matter falls in, the brighter the disk shines, the stronger the radiation pressure becomes, the harder it is for additional matter to fall in. Eventually, the quasar blows away its own fuel supply and shuts down. Yet even with this self-limiting behavior, the brightness of TON 618 remains overwhelming. It floods space with energy across billions of light years. And some of that energy channels into structures even more extreme. Jets, collimated beams of particles and radiation that shoot outward at nearly the speed of light. Perpendicular to the accretion disk, twin jets of matter blast outward from TON 618 at 99% the speed of light. These jets stretch for thousands of light years, carving tunnels through space and plowing into intergalactic gas like cosmic fire hoses. The jets form through a process involving magnetic fields and rotation. As the accretion disk spins, it drags magnetic field lines with it. These field lines twist and wrap around the black hole's rotational axis. Charged particles in the disk get caught in these spiraling magnetic fields and accelerated outward along the poles. Think of it like a cosmic railgun. The magnetic fields act as tracks. Particles ride those tracks, accelerating continuously, gaining energy from the rotation of the disk and the intense magnetic forces. By the time they shoot free from the immediate vicinity of the black hole, they are moving at relativistic speeds. The material in the jets is not solid. It is plasma, a superheated mix of electrons, protons, and other subatomic particles. These particles carry tremendous energy. Some individual particles have energies millions of times higher than anything achievable in human-built particle accelerators. They are cosmic rays, the most energetic particles in the universe. The jets are narrow, only a few light years across at their base, but they maintain coherence across enormous distances. Somehow, the magnetic fields keep them collimated, preventing them from spreading out and dissipating. This is one of the mysteries of astrophysical jets. The physics that confines them over such vast scales remains debated. When the jets slam into surrounding gas, they create shock waves. These shocks heat the gas to millions of degrees and generate radio emissions we can detect from Earth. TON 618's jets are so powerful that they excavate giant bubbles in the intergalactic medium, regions hundreds of thousands of light years across where normal gas has been blown away entirely. The energy carried by these jets is staggering. Estimates suggest TON 618's jets contain as much kinetic energy as the light emitted by millions of galaxies. They inject energy into the cosmos at a rate that can affect galaxy formation across vast regions. Gas that might otherwise collapse to form stars gets heated and dispersed by jet impacts. This phenomenon is called feedback. Supermassive black holes do not just passively consume matter, they actively regulate their own growth and the growth of their host galaxies. When a black hole feeds vigorously, the jets and radiation it produces blow away surrounding gas. This starves the galaxy of raw material for star formation and also starves the black hole of additional fuel. Over time, this feedback mechanism may be what prevents black holes from growing indefinitely. TON 618 is massive, but it cannot keep feeding forever. Eventually, it will exhaust nearby gas supplies or blow them away with radiation and jets. The accretion disk will fade, the jets will shut down, the quasar will go dark. But while the jets are active, they are among the most violent phenomena in the universe. The particles in those jets carry enough energy to strip electrons from atoms, ionize gas, and trigger shock waves. Anything caught in the path of a jet would be shredded instantly. Even at distances of thousands of light-years from TON 618, the jets remain dangerous. The orientation of jets matters. TON 618's jets point away from Earth. We see the black hole from an angle, viewing the accretion disk somewhat edge-on. If the jets were pointed directly at us, TON 618 would appear even brighter. Objects called blazars are quasars with jets aimed at Earth. They are the brightest, persistent objects we can observe. Fortunately, TON 618 is not a blazar, but even from a sideways view, the jets are detectable. Radio telescopes pick up emissions from the regions where the jets interact with surrounding matter. These observations reveal the jet's structure, speed, and composition. The jets also serve as evidence for the black hole's spin. Only rotating black holes can produce jets this powerful. The rotation stores energy in the space-time around the event horizon, energy that magnetic fields can tap and channel into the jets. This means TON 618 is not just massive, it is spinning, dragging space-time with it like a whirlpool. And this massive, spinning black hole appeared impossibly early. The timeline remains one of the biggest mysteries in cosmology. TON 618 existed when the universe was less than 3 billion years old. To put that in perspective, the universe is now 13.8 billion years old. TON 618 reached 66 billion solar masses in less than a quarter of the cosmos's current lifetime. That should be impossible. Black holes grow by consuming matter. Gas falls in. Stars get torn apart. The black hole gains mass. But there is a speed limit. The Eddington limit dictates how fast a black hole can feed. When matter accelerates toward the event horizon, friction heats it to extreme temperatures. That heat produces radiation. The radiation pushes outward. Eventually, the outward radiation pressure balances the inward gravitational pull. Matter cannot fall in faster. The black hole has maxed out its feeding rate. For a black hole eating at the Eddington limit continuously, you can calculate how long it takes to reach a certain mass. Starting from a stellar mass black hole, maybe 10 times the mass of our star, and feeding continuously at maximum rate, you get roughly 1 billion solar masses after 3 billion years. TON 618 weighs 66 times that amount. Even if you assume the black hole started much bigger, maybe from a direct collapse of a massive gas cloud instead of a single star, the math does not work. There has not been enough time. Some astrophysicists propose super-Eddington accretion. Maybe under certain conditions, black holes can exceed the Eddington limit and feed faster. Dense environments with lots of gas, collisions between galaxies, these events might temporarily boost the feeding rate. But even generous estimates of super-Eddington growth struggle to produce something as massive as TON 618 so quickly. Another theory involves primordial black holes. These would have formed in the first moments after the Big Bang from overdense regions of space, collapsing directly into black holes before stars even existed. If TON 618 started as a primordial black hole with a mass of millions or billions of solar masses, it would have a head start. The problem is, we have no direct evidence primordial black holes exist. They remain theoretical. And even if they do exist, getting one to grow into TON 618 still requires aggressive feeding over billions of years. Mergers offer another path. If multiple supermassive black holes in a dense cluster collided and merged, they could combine their masses into a single monster. Early galaxies were smaller and more densely packed. Collisions were common. Maybe TON 618 is the product of dozens or hundreds of mergers. But mergers are violent. They produce gravitational waves, ripples in space-time. We have detected gravitational waves from black hole mergers, but only from smaller black holes. A merger creating something like TON 618 would produce waves detectable across the universe. We have not seen evidence of such events in the early universe yet, though our instruments may not be sensitive enough. The formation mystery deepens when you consider that TON 618 is not alone. Other extremely massive black holes have been found in the early universe. Phoenix A, S50014 plus 81, SDSS J100 plus 2802, all of them contain supermassive black holes that formed impossibly early. This suggests we are missing something fundamental about how black holes grow. One possibility is that the early universe was more conducive to rapid black hole growth than current models predict. Gas densities might have been higher. Star formation might have happened faster. The first galaxies might have been more compact, funneling gas towards central black holes more efficiently. Dark matter could also play a role. We know dark matter exists because its gravity affects galaxy rotation and light bending, but we do not know what it is. Some theories propose interactions between dark matter and normal matter that could enhance black hole growth in the early universe. These interactions might not happen today, or they might be too weak to detect. Whatever the explanation, TON 618 challenges our understanding of cosmic evolution. It represents a phase of the universe we barely comprehend. The early cosmos was wilder and more extreme than our comfortable modern universe. Supermassive black holes appeared fast, grew fast, and shaped galaxy formation in ways we are only beginning to unravel. And TON 618 did not form in isolation. It sits at the center of a galaxy, a swarm of billions of stars trapped in its gravitational grip. TON 618 does not float alone in empty space. It sits at the heart of a galaxy, anchoring billions of stars in its gravitational field. Those stars orbit the black hole at immense distances, never getting close enough to be consumed, but forever bound to the monster at the center. The galaxy itself is difficult to see. The quasar at its core outshines everything else. Imagine trying to spot a candle flame while staring directly at a searchlight. The stars in the galaxy emit light, but their combined output is a tiny fraction of the blinding glare from the accretion disk. Telescopes struggle to resolve the galaxy's structure through the overwhelming brightness. What we can determine is that the galaxy must be massive. Black holes and their host galaxies follow a relationship. Bigger galaxies tend to have bigger central black holes. The correlation is not perfect, but it is strong. A black hole as massive as TON 618 likely sits in a galaxy weighing trillions of solar masses. Stars in that galaxy live under bizarre conditions. The gravitational influence of TON 618 extends across light years. Orbits near the galactic center would be fast and chaotic. Stars would whip around the black hole at thousands of miles per second. Collisions between stars would be common in the dense core. Close encounters would fling some stars into interstellar space while sending others spiraling toward the black hole. Any planetary systems in that galaxy would face existential challenges. Gravitational perturbations from the black hole and from neighboring stars would destabilize orbits. Planets could be ejected from their systems or sent crashing into their stars. Life would struggle to establish itself in such a violent environment. The radiation from TON 618's accretion disk and jets would bathe the entire galaxy in high-energy particles. X-rays and gamma rays would sterilize planets, stripping away atmospheres and destroying any complex molecules. Even worlds orbiting far from the galactic center would receive dangerous doses of radiation, yet the galaxy survives. Stars continue to orbit. Gas clouds persist in the outer regions beyond the reach of the black hole's immediate influence. The galaxy is not being destroyed. It is coexisting with the monster at its heart, albeit uneasily. This coexistence reveals something important. Supermassive black holes and galaxies grow together. They influence each other. The black hole regulates star formation through feedback. The jets and radiation from the accretion disk heat gas and prevent it from collapsing into new stars. This limits the galaxy's growth, but the galaxy also feeds the black hole. Gas from dying stars, from collisions, from tidal interactions with neighboring galaxies, all of it can funnel toward the center. The galaxy provides the fuel that keeps the quasar burning. Over billions of years, this relationship evolves. When the galaxy is young and gas-rich, the black hole feeds vigorously. The quasar shines brightly. Feedback kicks in, blowing away gas and shutting down star formation. The galaxy ages. The quasar fades. Millions or billions of years later, a merger with another galaxy delivers fresh fuel. The black hole awakens. The cycle repeats. TON 618 appears to be in an active phase right now. Or rather, it was 10 billion years ago when the light we see today began its journey. The galaxy is feeding the black hole. The black hole is shining, but this will not last forever. Eventually, the galaxy will exhaust its gas supply. The accretion disk will thin and disappear. TON 618 will go dark. The black hole will still exist, still holding 66 billion solar masses, but it will be invisible. A silent gravitational anchor at the center of a quiescent galaxy. And if you were unlucky enough to fall toward that anchor, if you somehow found yourself descending past the point of no return, the black hole would tear you apart in the most brutal way imaginable. Not through crushing gravity alone, through something far stranger, tidal forces that stretch you like taffy. Tidal forces are the difference in gravitational pull between 2 points. Stand on Earth, and gravity pulls your feet slightly harder than your head because your feet are closer to the planet's center. The difference is tiny, unmeasurable by human senses. Near TON 618, that difference becomes lethal. Imagine falling toward the black hole feet first. Your feet are closer to the singularity than your head. Gravity pulls your feet harder. The force differential stretches you. Near a stellar mass black hole, this stretching would rip you apart long before you reach the event horizon. Your body would elongate like spaghetti, hence the term spaghettification. TON 618 is different. Its event horizon is so large that the tidal gradient is much gentler. Gravity drops off more slowly across such immense distances. You could cross the event horizon intact. Your body would stretch, but not violently. Not yet. The real horror begins after crossing. As you fall inward from the event horizon toward the singularity, the tidal forces intensify. The 40 billion mile journey from the event horizon to the center takes time, even at increasing velocities. Along that journey, the stretching accelerates. First, you would feel a pulling sensation, uncomfortable but bearable. Your spine would lengthen slightly, then the pull would strengthen. Your bones would creak, joints would separate. The stretching would become painful. As you fell deeper, the forces would exceed what your body could withstand. Ligaments would tear, muscles would rip, bones would snap. But you would not die from the pain. There would not be time. The stretching would accelerate faster than your nerves could transmit signals. Eventually, the tidal forces would overcome molecular bonds. Your body would disintegrate into cells. Then the cells would rupture. Molecules would separate. Atoms would pull apart. You would be reduced to a stream of subatomic particles falling toward the singularity. This process is not unique to humans. Anything falling into TON 618 experiences the same fate. Stars, planets, asteroids, gas clouds. All of them stretch and shred. The difference is scale. A planet takes longer to spaghettify than a human because it is larger, and the tidal gradient must stretch across a bigger object. For TON 618, entire stars can cross the event horizon before being destroyed. A star falling toward the black hole might survive the initial crossing. It would continue to shine, pulled inward by gravity. But as it approached the singularity, tidal forces would overcome the star's own gravity. The star would elongate, forming a stream of hot gas spiraling into the black hole. We can observe this happening around smaller black holes. Events called tidal disruption events occur when a star wanders too close to a supermassive black hole. The tidal forces shred the star. Half the star's mass falls into the black hole. The other half gets flung outward. The process creates a bright flare of radiation we can detect from Earth. TON 618 likely experiences tidal disruption events regularly. Its gravitational reach is so large that stars from across the galaxy occasionally wander too close. Each disruption adds mass to the black hole and produces a burst of light from 10 billion light-years away. We cannot resolve individual disruptions, but they contribute to the overall luminosity we measure. The spaghettification process reveals the true violence of gravity. We think of gravity as a gentle force, the thing that keeps us grounded, makes apples fall, holds planets in orbit. Near black holes, gravity becomes a weapon. It tears reality apart at the seams. But even spaghettification is not the strangest effect near TON 618. There is a region closer to the event horizon where light itself cannot escape, a zone where photons orbit the black hole in circles before falling in or escaping, the photon sphere. The event horizon is where escape velocity equals the speed of light. But there is another boundary closer in, the photon sphere. This is where gravity is strong enough to bend light into circular orbits around the black hole. For TON 618, the photon sphere sits at 60 billion miles from the center, 1.5 times the radius of the event horizon. At this distance, a photon traveling tangent to the black hole will orbit indefinitely in a perfect circle, neither falling in nor escaping. This creates impossible optical effects. If you hovered just outside the photon sphere and looked sideways, perpendicular to the black hole, you would see light that had orbited multiple times. You could see the back of your own head. Photons leaving the back of your skull would curve around the black hole and enter your eyes from the front. The photon sphere is unstable. Any slight deviation inward and the photon falls toward the event horizon. Any deviation outward and it escapes to infinity. Real photons do not stay in the photon sphere long. They orbit once, maybe twice, then choose a fate. But the boundary represents a critical point in the geometry of space-time around the black hole. Light orbiting in the photon sphere is redshifted from the perspective of a distant observer. The photons lose energy climbing out of the gravity well. Colors shift toward the red end of the spectrum. If you watched light orbiting in the photon sphere from a safe distance, it would appear dimmer and redder than it should. Closer to the photon sphere than the event horizon lies another region called the ergosphere. This exists only around rotating black holes. Inside the ergosphere, space-time itself is dragged around the black hole. Frame dragging, the effect is called space rotates. If you tried to hover stationary in the ergosphere, you would fail. Space-time is moving. You would be forced to orbit in the same direction as the black hole's rotation. You could still escape the ergosphere if you had enough thrust. It is outside the event horizon, but you could not stand still. The ergosphere represents a region where the black hole's rotation has warped space-time so severely that remaining stationary becomes physically impossible. The geometry of space demands motion. This is not a limitation of technology or engine power. It is a fundamental consequence of general relativity. For TON 618, both the photon sphere and ergosphere would extend across distances comparable to planetary orbits in our solar system. Neptune orbits at roughly 2.8 billion miles from our star. The photon sphere of TON 618 is more than 20 times farther from the black hole's center. These are not compact regions. They span cosmic distances. Imagine a civilization with technology to approach the photon sphere. They could harvest energy from the black hole using a process called the Penrose mechanism. By dropping matter into the ergosphere at the right angle, they could extract rotational energy from the black hole. The matter would split, with one piece falling in and the other escaping with more energy than it started with. This is not science fiction. The physics is sound. A sufficiently advanced civilization could theoretically use a rotating black hole as a power source. The energy available is staggering. A black hole like Ton 618 stores rotational energy equivalent to a significant fraction of its rest mass. Tapping even a tiny percentage would provide power beyond anything achievable with stars or fusion reactors. But approaching the photon sphere would be dangerous beyond measure. Tidal forces, intense radiation from the accretion disk, frame dragging effects, and the ever-present risk of falling past the point of no return. One navigational error and you cross the event horizon. One thruster failure and you spiral inward. What would that final journey look like? What would you see as you fell into Ton 618, past the photon sphere, through the event horizon, toward the singularity? The first thing you would notice is the distortion. As you approached Ton 618, light from the universe behind you would bend around the black hole. Stars would appear to shift position. The black hole would loom ahead, but you would not see it. You would see an absence, a perfect circle of darkness against the background of space. Around that darkness, the accretion disk would blaze. Not a simple ring, but a warped, twisted structure. Light from the far side of the disk would curve around the black hole and reach your eyes. You would see both the front and back of the disk simultaneously. The disk would appear to wrap around the black hole sphere, creating a halo of light. Colors would shift. Light climbing toward you from deeper in the gravity well would be red-shifted. Light from higher regions would be blue-shifted. The disk would display a gradient of colors. Reds near the center, where gravity is strongest. Blues toward the edges, where space is flatter. As you fell closer, the black circle would grow. It would consume more of your field of view. The disk would appear to rise up around you, curving overhead and below. Perspective would become meaningless. The normal rules of geometry would fail. Light from stars behind you would converge. You would see the entire universe compressed into a shrinking circle behind you. As you approached the event horizon, that circle would collapse to a point. The universe behind would vanish. Ahead, the event horizon would not look like a surface. It would look like a deepening void, a bottomless pit in space. No light escapes, so there is nothing to see. Just blackness, absolute and perfect. Crossing the event horizon would feel like nothing. No barrier, no sensation, just a mathematical boundary in space-time that you pass through like crossing an invisible line painted on the ground. You would still be intact, still conscious, still falling. But now, the singularity would no longer be a point in space. It would be a moment in time, an inevitable future event. No matter which direction you accelerated, you would move closer to it temporally, not spatially. The singularity is not a place you can avoid by turning left or right. It is a when, not a where. Looking back toward the universe outside, you would see time accelerate. Stars would move faster, planets would orbit rapidly, galaxies would spin and evolve. The entire future history of the universe would play out before your eyes in moments. This is gravitational time dilation in reverse. To observers outside, you appear frozen, slowing asymptotically as you approach the event horizon. But from your perspective, the universe speeds up. You are falling into the future faster than the rest of reality. The accretion disk would still be visible, but distorted. Light would bend in strange ways. You might see multiple images of the same structures. The geometry of space inside the event horizon is so warped that light paths loop and twist impossibly. As you fell deeper, tidal forces would begin their work. The stretching would start gently, then intensify. Your body would elongate. Pain would surge through you, but only briefly. The forces would escalate faster than your nervous system could process. Then disintegration. Your body would tear apart. Cells would separate. Molecules would break. Atoms would pull into a stream. You would become a thin line of particles, a thread spiraling toward the singularity. The final moments would be incomprehensible. Time and space would lose distinction. Cause and effect would tangle. The laws of physics as we understand them would break down. The singularity would approach a point of infinite density where all the mass of the black hole concentrates. And then nothing. The singularity would consume you. Whatever happens inside a singularity is unknown. Physics has no answers. General relativity predicts infinities, which usually means the theory has reached its limits. What does an outside observer see during all this? To someone watching from a safe distance, your fall into ton 618 would appear to last forever. Literally, you would never reach the event horizon from their perspective. You would slow down, freeze, and fade to black. This is not an optical illusion or a trick of light. It is a fundamental property of space-time. As you approach the event horizon, time for you, relative to the outside universe, slows down. The closer you get, the more extreme the effect becomes. At the event horizon itself, time dilation approaches infinity. From your perspective, the fall happens in finite time. You cross the event horizon in seconds or minutes. But from the outside observer's perspective, those seconds stretch. 1 second of your time becomes 2 seconds of theirs, then 10, then 1,000, then 1,000,000. The math is precise. Time dilation near a black hole depends on distance from the event horizon. There is a formula from general relativity that describes it. As you approach the boundary, the denominator in the equation approaches zero. The result grows without limit. Time slows to a crawl. Light carries information about your fall to the distant observer. Photons leaving your body must climb out of the gravity well. As you get closer to the event horizon, those photons take longer and longer to escape. They become increasingly redshifted, losing energy to gravity. The observer would see you slow down gradually. Your movements would become sluggish. Your descent would decelerate. You would appear to asymptotically approach the event horizon without ever quite reaching it. Your image would also fade. The photons from your body would redshift beyond the visible spectrum. First, you would turn red, then infrared, then radio waves. Eventually, the wavelength of light leaving you would stretch beyond what any detector could measure. You would become invisible, but you would never truly disappear from the outside observer's timeline. Technically, the last photons that carry information about you crossing the event horizon would take infinite time to reach them. You would be frozen at the boundary forever from their reference frame. This creates a paradox. You experience crossing the event horizon. You fall through, continue inward, and reach the singularity. But someone watching you never sees it happen. To them, you are stuck at the event horizon for eternity, gradually fading from view. Both perspectives are correct. There is no absolute time. Time is relative. It depends on your motion and the gravitational field you inhabit. What happens to you and what appears to happen to you from a distance can be different, and both are real. This effect applies to everything falling into ton 618. Stars, gas, dust, all of it appears to freeze at the event horizon from the perspective of a distant observer. The event horizon becomes a graveyard of images. Every object that ever fell in is still there, visually, forever stuck at the boundary. Of course, the redshift makes them invisible quickly, but mathematically, the information is still present. The event horizon accumulates a record of everything that crossed it, encoded in increasingly long wavelength photons that take increasing amounts of time to escape. This leads to another mystery. If nothing ever appears to cross the event horizon from an outside perspective, how does the black hole grow? The answer is that the event horizon expands. As matter approaches, the black hole's mass increases gradually, and the event horizon radius increases with it. The boundary grows outward to meet the infalling matter. From the outside, it appears as if matter gets absorbed by an expanding boundary rather than falling through a fixed one. Mathematically, the two descriptions are equivalent. The black hole gains mass either way. For an advanced civilization monitoring ton 618 from a distance, This time, dilation effect would make studying infalling matter nearly impossible. Probes sent toward the event horizon would appear to slow and freeze. Data transmission would redshift and slow. What takes seconds for the probe takes years for the observers. But what waits at the center of TON 618, beyond the event horizon, past the region where time and space trade places? The singularity, the ultimate unknown. At the center of TON 618, all 66 billion solar masses compress into a single point. Not a small object, not a dense sphere. A point with zero volume and infinite density. This is the singularity, and it is where physics breaks. General relativity predicts singularities inside black holes. The equations demand it. As matter collapses under its own gravity, with nothing to stop it, density increases without limit. The matter crushes down to a geometric point, where the curvature of space-time becomes infinite. Infinite density is a problem. Infinity in physics usually signals that your theory has reached its limits. It means the equations are giving nonsense answers. At the singularity, general relativity stops working. The predictions become meaningless. We do not know what actually happens at the singularity. Does matter truly compress to zero volume? Does it reach infinite density? Or does something else occur? Something that requires a theory of quantum gravity we do not yet possess. String theory, loop quantum gravity, and other attempts to merge quantum mechanics with general relativity suggest the singularity might not be infinitely small. Quantum effects might prevent complete collapse. There might be a minimum size, a Planck scale structure, tiny but not zero. The Planck length is 1.6 times 10 to the negative 35 meters. Unimaginably small, but not infinitely small. If quantum gravity prevents collapse below this scale, the singularity would be a Planck-sized object rather than a true point. Still incomprehensibly dense, but not infinite. Another possibility is that the singularity is not a point, but a ring. This applies to rotating black holes. When a black hole spins, the singularity is predicted to form a ring shape rather than a point. The math gets even worse here. General relativity predicts that spacetime inside a rotating black hole contains closed time-like curves, paths through spacetime that loop back on themselves, allowing time travel. No one believes these predictions are physically real. They are likely artifacts of the theory breaking down. But we have no observations to guide us. We cannot see inside event horizons. We cannot send probes to singularities and get data back. Everything that crosses the event horizon is lost to outside observers forever. This leads to the information paradox. In quantum mechanics, information is conserved. You cannot destroy information. But if matter falls into a black hole and reaches the singularity, where does the information about that matter go? Does it disappear? That would violate quantum mechanics. Stephen Hawking proposed that black holes evaporate over time through Hawking radiation. Quantum effects near the event horizon cause particle-antiparticle pairs to form. One particle falls in, the other escapes. The escaping particle carries energy away from the black hole. Over immense timescales, this process could cause the black hole to evaporate completely. But Hawking radiation is thermal. It is random. It carries no information about what fell into the black hole. If the black hole evaporates and disappears, the information is lost. This violates quantum mechanics. Hawking himself wrestled with this paradox for decades. Eventually, he conceded that information might be preserved somehow, perhaps encoded in the Hawking radiation in ways too subtle to detect. But the question remains unresolved. For TON 618, Hawking radiation is irrelevant on human timescales. The evaporation time for a black hole scales with the cube of its mass. Larger black holes evaporate slower. TON 618 is so massive that its Hawking radiation is negligible. It would take longer than 10 to the 100 years for TON 618 to evaporate completely. The universe is only 13.8 billion years old. Ton 618 will outlast stars, galaxies, and possibly time itself. The singularity at the heart of Ton 618 represents the edge of human knowledge. We know it exists because the math demands it. We know it hides behind an event horizon we can never see past. We know it is where physics as we understand it fails. What happens at a singularity is one of the greatest unsolved problems in theoretical physics. Answering it requires a theory that unifies quantum mechanics and gravity, something we do not yet have. Until then, the singularity remains a paradox, a mathematical abstraction hiding a truth we cannot grasp. And if black holes confuse us, the fact that Ton 618 will never evaporate makes things stranger still. Quantum mechanics predicts that black holes are not entirely black. They emit radiation, faint and cold, through a quantum process discovered by Stephen Hawking in 1974. This radiation carries energy away from the black hole. Over time, the black hole loses mass. Eventually, it evaporates completely. The mechanism involves virtual particles. Quantum field theory states that empty space is not truly empty. Particle-antiparticle pairs constantly pop into existence and annihilate each other almost instantly. Near the event horizon of a black hole, something strange happens. One particle falls into the black hole while its partner escapes. The escaping particle becomes real, carrying energy away. This energy must come from somewhere. It comes from the black hole's mass. Each escaping particle slightly reduces the black hole's total mass. The process is extraordinarily slow for large black holes, but it is real. Given enough time, any black hole will evaporate. The temperature of Hawking radiation depends on the black hole's mass. Smaller black holes are hotter, larger black holes are colder. A stellar mass black hole, weighing 10 times our star's mass, would have a temperature of billionths of a degree above absolute zero. Ton 618, weighing 66 billion solar masses, would be unfathomably colder. The temperature of Ton 618's Hawking radiation is so low that it is drowned out by the cosmic microwave background radiation, the leftover heat from the Big Bang. The universe itself is warmer than Ton 618's Hawking radiation. This means the black hole actually absorbs more energy from the cosmic background than it loses through Hawking radiation. It is growing, not shrinking. Only after the universe expands and cools enough would Ton 618 start losing mass. The cosmic microwave background temperature decreases as the universe expands. Eventually, billions of years from now, the background will cool below Ton 618's Hawking temperature. Then and only then would the black hole begin to evaporate. How long would evaporation take? The formula is brutal. Evaporation timescales with the cube of the mass. Double the mass, and evaporation takes 8 times longer. Ton 618 weighs 6.6 times 10 to the 10th solar masses. The evaporation time is proportional to that number cubed. Working through the math gives an evaporation timescale of roughly 10 to the 100 years. That is a 1 followed by 100 zeros. For comparison, the current age of the universe is about 10 to the 10th years. Ton 618 will take 10 to the 90 years longer than the universe has currently existed to evaporate. By that time, all stars will have burned out. Galaxies will have dispersed. Protons may have decayed. The universe will be a cold, dark, expanding void. Ton 618 will be one of the last structures remaining, a frozen monument to gravity's dominance. As it finally evaporates, the process accelerates. Smaller black holes radiate faster. The last stages of evaporation happen quickly. Ton 618 would spend nearly all its lifetime barely radiating, then suddenly flash into nothing in the final moments. But that final flash is unimaginably far in the future. Humans will be extinct. Earth will be gone. Our star will have died and dispersed. The Milky Way will have merged with other galaxies and aged beyond recognition. Life, if it exists anywhere, will have moved to unimaginable form. Hawking radiation reveals something profound. Black holes are not eternal. They are temporary structures, albeit ones that last far longer than anything else in the universe. Even TON 618, the most massive black hole known, will eventually succumb to quantum effects and vanish. But the evaporation process ties into the information paradox. If a black hole evaporates, what happens to the information about everything that fell in? Hawking radiation is thermal and random. It does not encode specific information about infalling matter. When the black hole disappears, does the information disappear too? This violates quantum mechanics, which says information cannot be destroyed. Somehow, the information must be preserved. Maybe it is encoded in the Hawking radiation in subtle ways we do not yet understand. Maybe it escapes through mechanisms we have not discovered. The paradox remains unsolved. For now, TON 618 sits in distant space, massive and stable, radiating nothing measurable. It will outlast everything we know, and long before it evaporates, it will reveal other mysteries about how information behaves in the most extreme gravitational fields imaginable. Information in physics is not just data on a hard drive. It is a fundamental property of the universe. Every particle, every interaction, carries information about its state, history, and quantum properties. Quantum mechanics says this information is conserved. It can be scrambled, hidden, or transformed, but never destroyed. Black holes challenge this rule. When matter crosses the event horizon, it vanishes from the observable universe. Outside observers can never retrieve it. The matter carries information, quantum states, particle configurations, historical data about where it came from. All of that disappears behind the event horizon. If black holes truly destroy information, they violate quantum mechanics. This would be catastrophic for physics. Quantum theory is one of the most successful frameworks ever developed. Breaking it requires extraordinary evidence. The paradox deepens with Hawking radiation. If black holes evaporate over time, eventually they disappear completely. When TON 618 finally evaporates 10 to the 100 years from now, where does all the information about the 66 billion solar masses that formed it go? Hawking radiation is thermal. It is random blackbody radiation determined only by the black hole's mass, charge, and spin. It does not encode specific information about what fell in. A black hole formed from antimatter would emit the same Hawking radiation as one formed from matter if the masses were equal. This suggests information is lost. Everything that ever fell into TON 618 over billions of years would be erased when the black hole evaporates. Stars, gas, photons, entire civilizations, if any existed nearby, all of it reduced to generic thermal radiation. Hawking originally believed information was destroyed. The black hole interior is causally disconnected from the outside universe. Whatever happens at the singularity is hidden. When the black hole evaporates, that information is simply gone. But this conclusion bothered physicists. If black holes destroy information, then quantum mechanics is wrong, or at least incomplete. The laws of physics would have exceptions. This seemed unacceptable. In the decades since Hawking proposed his radiation, researchers have suggested many solutions. One idea is that information is encoded in the Hawking radiation in subtle correlations between particles. The radiation only appears thermal. Hidden within it is information about what fell in, encoded in quantum entanglement patterns too complex to measure directly. Another proposal involves black hole remnants. Maybe black holes do not evaporate completely. When they shrink to a certain size, quantum gravity effects halt the evaporation. A tiny remnant remains, containing all the information. TON 618 would eventually shrink to a Planck mass remnant, an object weighing about 22 micrograms, but packed with information about its 66 billion solar mass history. Some physicists suggest information never enters the black hole at all. It gets encoded on the event horizon. The horizon's surface area grows when matter falls in. Information might be stored as a hologram on the two-dimensional surface. When the black hole evaporates, the information is released back into space. This holographic principle has gained traction. It suggests the entire three-dimensional volume of space inside the event horizon can be described by information on the two-dimensional surface. The universe might be holographic at the deepest level. For TON 618, the event horizon has a surface area calculable from its radius. That surface area is enormous, measured in square light years. If information is encoded there, the horizon could store unimaginable amounts of data. Every particle that ever crossed would leave a microscopic imprint. Another possibility is that information escapes through mechanisms we have not discovered. Maybe there are channels, quantum tunnels, or other paths by which information leaks out gradually. The evaporation process might be more complex than simple thermal radiation. Or perhaps the paradox reveals a deeper flaw in how we think about space-time. Maybe the interior of a black hole is not a separate region of space-time. Maybe it is connected to other parts of the universe through structures we cannot detect. Wormholes, baby universes, higher dimensions. Any of these could resolve the paradox. The stakes are high. Solving the information paradox would revolutionize physics. It would require unifying quantum mechanics and general relativity, the two great theories of the 20th century that remain incompatible. TON 618 represents an extreme laboratory for testing these ideas. Its massive scale, long lifetime, and powerful gravitational effects make it a natural proving ground. Understanding what happens to information in a black hole this large could unlock secrets about the nature of reality itself, and compared to the black hole at our galaxy's center, TON 618 is incomprehensibly more massive. At the heart of the Milky Way, 26,000 light-years from Earth, sits a supermassive black hole called Sagittarius A star. It weighs 4 million solar masses. Its event horizon measures roughly 17 million miles across. We orbit this black hole, our entire solar system, our star, every planet, all of us. We circle Sagittarius A star at a safe distance. It sounds massive. 4 million times the mass of our star concentrated into a region smaller than Mercury's orbit. The gravity is strong enough to hold 200 billion stars in a galactic disk. Sagittarius A star is the gravitational anchor of our home galaxy. Now compare it to TON 618. TON 618 weighs 66 billion solar masses. That is 16,500 times more massive than Sagittarius A star. If you placed both black holes side by side, Sagittarius A star would be a marble. TON 618 would be a cathedral. The event horizon comparison is even more dramatic. Sagittarius A star's event horizon spans 17 million miles. You could fit it comfortably inside Mercury's orbit with room to spare. TON 618's event horizon stretches 40 billion miles. You could place 2,350 copies of Sagittarius A star's event horizon inside TON 618's boundary. Think about what this means for scale. Our entire galaxy orbits a marble. TON 618 is the cathedral. If TON 618 sat at the center of the Milky Way, its event horizon would extend past Neptune. The entire solar system would be inside the point of no return. But mass and size are not the only differences. Sagittarius A star is relatively quiet. It does not feed aggressively. Gas near the galactic center is sparse. The black hole occasionally consumes a cloud or a star that wanders too close, producing brief flares of radiation. Most of the time, it is dormant. TON 618 is in an active feeding phase. It consumes 10 solar masses of material per year. Its accretion disk blazes with the light of 400 trillion stars. The difference in brightness is staggering. Sagittarius A star emits modest amounts of radiation, TON 618 outshines entire galaxy clusters. We can observe Sagittarius A star directly. Telescopes can track stars orbiting it. We measure their velocities, calculate their orbits, and determine the black hole's mass precisely. One star, called S2, completes an orbit every 16 years. At closest approach, it reaches speeds of 5,000 kilometers per second, about 2% the speed of light. TON 618 is too distant for such observations. We cannot resolve individual stars near it. We cannot track orbits. We infer its mass from the brightness of the quasar and the dynamics of surrounding gas. The measurements are less precise but still reliable. Multiple independent methods confirm the 66 billion solar mass figure. Another difference lies in accessibility. Sagittarius A star is in our neighborhood, cosmically speaking. 26,000 light-years is close. We can study it with current technology. Future missions might send probes to observe it up close, though the journey would take tens of thousands of years. TON 618 sits 10 billion light-years away. The light we see left that object when the universe was less than 3 billion years old. We are looking back in time, witnessing the early universe. We will never visit TON 618. We will never send probes there. The distance is too vast. The journey would take longer than the universe has existed. Yet studying TON 618 from afar teaches us things Sagittarius A star cannot. TON 618 represents an extreme case. It shows us what black holes can become under the right conditions. It reveals the upper limits of mass and size. It challenges our theories of formation and growth. Sagittarius A star is comfortable, familiar, and relatively safe. It is our galactic anchor, massive but manageable. TON 618 is alien, distant, and incomprehensibly extreme. It is a reminder that the universe contains objects far beyond human scale, and despite its overwhelming brightness in the past, from Earth, TON 618 appears as nothing more than a faint smudge. Distance and cosmic expansion hide this monster in plain sight. TON 618 shines with the power of 400 trillion stars, yet from Earth it appears as a faint dot, barely visible even with powerful telescopes. The discrepancy between intrinsic brightness and apparent brightness reveals the immense scale of cosmic distances. Light follows the inverse square law. Double the distance, and brightness drops to 1/4. Triple the distance, and brightness falls to 1/9. The relationship is brutal. Small increases in distance cause massive decreases in apparent brightness. TON 618 sits 10 billion light-years away. That is 10 billion times 9.5 trillion kilometers. The light we see today left TON 618 when the universe was less than 3 billion years old. It has been traveling through space for 10 billion years, crossing incomprehensible distances. Over that journey, the light spreads out. Photons that left TON 618's accretion disk in a narrow beam diverge. By the time they reach Earth, they are scattered across a huge area. The photons per square meter reaching Earth are incredibly sparse. Only a tiny fraction of TON 618's total light output hits our telescopes. But distance alone does not explain the dimness. There is another factor: redshift. The universe is expanding. Space itself stretches. As light travels through expanding space, its wavelength stretches with it. Longer wavelengths mean lower energy. The light becomes redder. TON 618's redshift is extreme. The universe has expanded significantly since the light we see left the quasar. Wavelengths have stretched by a factor of several times. What was once high-energy ultraviolet or X-ray light has been shifted into the visible or infrared spectrum. This redshift reduces the energy of each photon. It also reduces the rate at which photons arrive. Time dilation from cosmic expansion means the photons are spread out temporally as well as spatially. The combination makes TON 618 appear far dimmer than it would if it were nearby and stationary. Calculating the apparent magnitude involves accounting for both distance and redshift. Astronomers use a measure called absolute magnitude to compare intrinsic brightness. TON 618 has an absolute magnitude of around -30. For reference, our star has an absolute magnitude of about +4.8. Lower numbers mean brighter objects. -30 is extraordinarily bright. But apparent magnitude, what we actually see, is around +16. That is faint. You need a decent amateur telescope to see it. It looks like a dim star, unremarkable and easy to miss. Without spectroscopy and detailed analysis, you would never guess it was the most luminous object in that region of sky. The atmosphere also interferes. Light from TON 618 passes through Earth's atmosphere before reaching telescopes. The atmosphere absorbs some wavelengths and scatters others. Turbulence blurs the image. Ground-based observations are limited. Space telescopes like Hubble provide clearer views, but even they struggle to resolve details at such distances. Dust in the Milky Way adds another layer of dimming. Light from TON 618 must pass through our galaxy to reach us. Interstellar dust absorbs and scatters light, particularly blue wavelengths. This makes distant objects appear redder and dimmer than they actually are. Astronomers must correct for this extinction when calculating true brightness. Despite all these factors, TON 618 remains detectable. Modern telescopes and instruments are sensitive enough to pick up its faint signal. Spectroscopy reveals its nature. The light signature shows emission lines from hot gas. The redshift indicates enormous distance. The luminosity calculations point to a supermassive black hole. Discovering TON 618 required careful observations and analysis. Marie-Helene Ulrich noticed it as a faint smudge and catalogued it. Decades later, better technology revealed its true nature. This pattern repeats across astronomy. Many extraordinary objects hide in plain sight, too distant to recognize without advanced instruments. There may be others like TON 618, even more massive, even more distant, waiting to be found, or they may have already been found and catalogued as unremarkable points of light, their secrets hidden until someone looks closer. TON 618 exists in a special era of cosmic history, the quasar era, a time when the universe was young and violent and supermassive black holes blazed across the sky. 10 billion years ago, the universe looked different. Galaxies were smaller, closer together, and colliding frequently. Gas was denser, star formation rates were higher, and supermassive black holes like TON 618 dominated the sky, shining as quasars. The quasar era began roughly 1 billion years after the Big Bang and peaked around 3 billion years. During this time, supermassive black holes actively fed on abundant gas and dust. Accretion disks blazed. Quasars outnumbered and outshone everything else in the universe. Today, quasars are rare. Most supermassive black holes are dormant. They sit at galaxy centers, massive but dark, starved of fuel. The universe has aged. Galaxies have spread apart. Gas has been consumed by star formation or heated and dispersed. Black holes have less to eat. TON 618 represents a snapshot of that ancient era. When we look at it, we see the universe as it was 10 billion years ago. The light reaching us today left TON 618 when quasars were common. The view is a window into cosmic history. Back then, galaxy mergers were frequent. Small galaxies crashed together, combining their mass and funneling gas toward their central black holes. These mergers triggered intense star formation and quasar activity. The black holes gorged themselves on infalling material. The quasar era shaped galaxy evolution. Feedback from quasars, the radiation and jets they produced, heated surrounding gas and prevented it from collapsing into stars. This limited galaxy growth. Without quasar feedback, galaxies would be much larger today. They would have converted more of their gas into stars. But quasars also enrich the intergalactic medium. Jets ejected heavy elements created by stars into the space between galaxies. These elements, carbon, oxygen, nitrogen, iron, spread across vast distances. Later generations of stars and planets formed from this enriched material. TON 618 contributed to this process. Its jets carried heavy elements thousands of light years into intergalactic space. The radiation from its accretion disk ionized hydrogen across enormous volumes, creating bubbles of hot, ionized gas. Observing quasars like TON 618 helps astronomers understand the early universe. The abundance of heavy elements in quasar spectra reveals how quickly stars formed and enriched their environments. The clustering of quasars shows how matter was distributed. The evolution of quasar luminosity over time tracks how black holes grew and when they shut down. One mystery is why the quasar era ended. Why did supermassive black holes stop feeding so vigorously? The answer involves multiple factors. Gas supplies decreased as star formation consumed available material. Quasar feedback pushed remaining gas away. Galaxy mergers became less frequent as the universe expanded and galaxies separated. Additionally, the most massive black holes may have simply eaten everything nearby. A black hole like TON 618 has a sphere of influence extending light years. Once it consumes or ejects all the gas within that region, it starves. Fresh fuel requires a major event like a galaxy merger. The transition from the quasar era to the modern universe was gradual. Quasar activity peaked and declined over billions of years. By the time the universe was 6 or 7 billion years old, most quasars had faded. Today, only a small fraction of supermassive black holes are actively feeding. Yet the era left a lasting impact. The distribution of galaxies we see today was shaped by quasar feedback. The intergalactic medium carries the chemical fingerprints of that ancient activity. The supermassive black holes themselves remain, dormant monuments to a more violent past. TON 618 may have shut down by now. The light we see is 10 billion years old. In the present day, wherever TON 618 exists in the current universe, it might be dark and quiet. The accretion disk may have dissipated. The quasar may have faded. We have no way to know without waiting for light from the present-day TON 618 to reach us, which will not happen for another 10 billion years. This is the strange nature of astronomical observation. We see the past, not the present. The universe is a museum of history. Every observation is a glimpse of what was, not what is. And during its active phase, TON 618 consumed an unimaginable amount of matter. Stars, gas, entire systems, all devoured by the monster at the center. 66 billion solar masses did not accumulate from nothing. Every kilogram of mass in TON 618 came from somewhere. Gas clouds, dust, planets, and stars, all consumed over billions of years. Calculating how many stars fell into the black hole reveals the scale of destruction. Assume TON 618 grew primarily by consuming gas rather than whole stars. Gas accretion is more efficient. Stars are discrete objects that might get flung away by gravitational interactions before falling in. Gas forms a smooth accretion disk that spirals inward continuously. But some stars inevitably fell in. Close encounters with the black hole would disrupt stellar orbits. Tidal forces would shred stars that ventured too close. The disrupted material would join the accretion disk. Over billions of years, this adds up. A rough estimate requires assumptions. Suppose 10% of TON 618's mass came from actual stars rather than diffuse gas. That is 6.6 billion solar masses worth of stars. If the average star weighs half the mass of our star, a reasonable estimate given that most stars are smaller red dwarfs, then TON 618 consumed roughly 13 billion stars. 13 billion stars, each one a fusion reactor, shining for billions of years, potentially hosting planets, possibly harboring life, all of them torn apart and swallowed by the black hole. The number could be much higher. If TON 618 formed in a dense stellar environment, a compact cluster where stars crowded together, stellar consumption rates would increase. Collisions between stars would be common. The black hole would act like a gravitational vacuum, sweeping up debris. Each stellar disruption event is violent. As a star approaches the black hole, tidal forces stretch it. The near side experiences stronger gravity than the far side. The star elongates into a stream. Part of the stream falls into the black hole. Part gets flung outward at high velocity. The infalling material heats to millions of degrees. It emits intense X-rays and ultraviolet radiation. For weeks or months, the disrupted star shines brightly before fading. We observe these tidal disruption events in other galaxies. They are spectacular but brief. TON 618 has likely experienced millions or billions of these events. Each one adds mass. Each one releases energy. Cumulatively, tidal disruptions contribute to the black hole's growth and luminosity. But most of TON 618's mass probably came from gas. The early universe contained vast amounts of primordial hydrogen and helium. This gas had not yet formed stars. It filled the space between galaxies and within galaxy halos. Black holes could accrete it directly. Simulations suggest supermassive black holes grow primarily through two channels. Cold gas flows during the early universe, when gas streams toward galaxy centers along cosmic filaments, and galaxy mergers, which disturb gas and funnel it inward. TON 618 benefited from both. It formed in the early universe when cold flows were active. It likely experienced multiple major mergers that delivered fresh fuel. The combination allowed rapid growth. Even with efficient gas accretion, TON 618 needed billions of years to reach its current mass. Feeding at the Eddington limit, the theoretical maximum rate, a black hole can double its mass every 50 million years. Starting from 1 million solar masses, you can reach 66 billion solar masses in about 15 doubling periods, or roughly 750 million years. But TON 618 appeared when the universe was less than 3 billion years old. That gives enough time, barely. If everything went perfectly, the black hole had to start big, feed continuously, and possibly exceed the Eddington limit at times. The stars and gas consumed by TON 618 represent raw material that could have formed galaxies, planets, and life elsewhere. Instead, they crossed the event horizon and added to the black hole. The gravitational influence of TON 618 diverted matter from other fates, yet the destruction is not entirely one-sided. The energy released during accretion, the jets and radiation, enriched the surrounding universe. Heavy elements created in stars that were consumed got ejected into space. The feedback regulated galaxy formation across vast regions. TON 618 shaped its cosmic neighborhood not just by consuming matter, but by pushing it around, heating it, and redistributing it. The sphere of influence extended far beyond the event horizon. The event horizon marks the boundary of no return, but the black hole's gravitational influence extends far beyond. The sphere of influence is the region where the black hole's gravity dominates over the collective gravity of surrounding stars and gas. For TON 618, this sphere stretches across light years. Inside the sphere of influence, orbits are determined by the black hole, not by the galaxy as a whole. Stars orbit the central mass directly. Their trajectories follow Keplerian orbits, ellipses, or hyperbolas dictated by the black hole's immense gravity. Outside the sphere, the galaxy's overall mass distribution dominates. Stars orbit the galactic center, but feel the influence of all the mass around them. The black hole is just one component among many. The size of the sphere of influence depends on the black hole's mass and the surrounding stellar density. A more massive black hole has a larger sphere. Lower stellar density means the sphere extends farther. The formula involves the black hole mass, stellar velocity dispersion, and galaxy properties. For TON 618, calculations suggest the sphere of influence extends several light years from the center. Compare this to Sagittarius A star, where the sphere of influence is only a few light months across. TON 618's influence is hundreds of times larger. Within this region, stars experience extreme conditions. Orbital velocities are high. Close approaches to the black hole are common. Gravitational interactions with other stars happen frequently. The environment is chaotic and violent. Some stars have stable orbits, circling the black hole at safe distances. Others have eccentric orbits that bring them dangerously close at periapsis before swinging back out. A few unlucky stars have plunging orbits that cross the event horizon directly. The density of stars within the sphere of influence is much higher than in typical galaxy regions. Gravity concentrates matter toward the center. This creates a stellar cusp, a region where star density increases sharply as you approach the black hole. In this cusp, stellar collisions are possible. Two stars on crossing orbits might collide, merging or shattering. The debris would heat and glow briefly before dispersing. Some of this debris would fall toward the black hole, contributing to the accretion disk. Planets within the sphere of influence face precarious futures. Gravitational perturbations from the black hole and from passing stars would destabilize planetary orbits. Planets could be ejected from their star systems entirely or sent crashing into their stars. Long-term stability is unlikely. Any civilization living within TON 618's sphere of influence would face existential challenges. The sky would be crowded with stars, far more than we see from Earth. Gravitational interactions would make long-term planning difficult. Orbits would change over thousands or millions of years. The radiation environment would be harsh. If TON 618 is actively feeding, the accretion disk and jets would flood the region with X-rays and high-energy particles. Atmospheres would be stripped. Surface life would be sterilized. Only shielded underground habitats might survive. Yet the sphere of influence also offers opportunities. Stars are closer together, making interstellar travel easier. The dense environment might allow advanced civilizations to harvest resources from multiple star systems. The black hole itself could serve as a gravitational slingshot, accelerating spacecraft to high velocities. Observing the sphere of influence from Earth is impossible. TON 618 is too distant. We cannot resolve individual stars. We see only the integrated light from the galaxy and the overwhelming glare from the quasar. Detailed structure remains hidden, but we can infer what the region looks like from observations of other galaxies. Nearby galaxies with supermassive black holes show similar structures. Dense stellar cusps, high-velocity stars, occasional tidal disruption events. TON 618 likely displays these features, but on a scale orders of magnitude larger. The sphere of influence is not static. As the black hole consumes stars and gas, its mass increases. The sphere expands. More stars fall under direct gravitational control. The process is slow but relentless. Over billions of years, the sphere of influence can grow to encompass significant fractions of the galaxy core. Eventually, the black hole's gravity could dominate the entire central region, restructuring the galaxy's interior. And within this zone of control, the black hole generates gravitational effects so strong that they produce ripples in space-time itself. Ripples that carry information across the universe at the speed of light. Gravitational waves are ripples in space-time caused by accelerating masses. When massive objects move, they distort the fabric of space and time around them. These distortions propagate outward at the speed of light, carrying energy and information about the event that created them. Black hole mergers produce the strongest gravitational waves. When two black holes spiral toward each other, they accelerate to tremendous velocities. The final moments before merger involve objects weighing millions or billions of solar masses moving at significant fractions of light speed. The space-time distortion is immense. Ton 618 likely formed through multiple mergers. A black hole this massive did not grow smoothly. It is the product of collisions between smaller supermassive black holes over billions of years. Each merger produced gravitational waves. When two supermassive black holes merge, the process takes millions of years. They start orbiting each other at large distances. Gravitational wave emission carries away energy and angular momentum. The orbits shrink. The black holes spiral inward. As they get closer, the orbital period decreases. The gravitational waves become stronger and more frequent. In the final seconds, the black holes plunge together. Space-time churns violently. The two event horizons merge into one. A single larger black hole remains, vibrating like a struck bell. This vibration, called ring-down, produces a characteristic gravitational wave signal. The frequency and decay rate depend on the final black hole's mass and spin. For a merger creating something like Ton 618, the ring-down would produce waves with periods of hours or days, far longer than the millisecond waves from stellar mass black hole mergers. Detecting gravitational waves from Ton 618's formation is beyond current technology. Our detectors, LIGO and Virgo, are sensitive to high-frequency waves from stellar mass black holes. Supermassive black hole mergers produce low-frequency waves that ground-based detectors cannot measure. Future space-based detectors like LISA, the Laser Interferometer Space Antenna, will target supermassive black hole mergers. LISA will launch in the 2030s and observe gravitational waves with periods of seconds to hours. It might detect mergers similar to those that built Ton 618, but the waves from Ton 618 itself are long gone. They were emitted billions of years ago. If a major merger created or significantly grew Ton 618 inches, the early universe, the gravitational waves from that event passed through Earth billions of years before the planet existed. Gravitational waves travel at light speed, so they cannot outpace the electromagnetic radiation from the same event. By the time we see the light from Ton 618, the gravitational waves have already arrived. We missed them. However, Ton 618 might still be producing weaker gravitational waves today. If it is consuming stars or gas in an asymmetric way, or if it is a binary system with another massive object, it could emit detectable waves. Some theoretical models suggest that supermassive black holes like Ton 618 could have binary companions, smaller black holes orbiting the main one. These binaries would emit continuous gravitational waves. Over time, the waves carry away energy, and the binary shrinks until the black holes merge. If Ton 618 has a massive companion, LISA might detect it. The signal would be faint, requiring years of observation. But detecting such a system would revolutionize our understanding of how supermassive black holes grow and interact. Gravitational wave astronomy is still young. LIGO made its first detection in 2015. Since then, we have observed dozens of stellar mass black hole mergers and neutron star collisions. Each detection reveals new physics. Supermassive black hole mergers represent the next frontier. These events are rare but spectacular. The gravitational wave signals encode information about the black hole masses, spins, and the properties of space-time itself. Detecting them will test general relativity in the strongest gravity regime possible. Ton 618 stands as a reminder of what is out there, waiting to be found. The universe is full of massive black holes colliding, merging, and emitting waves that wash over Earth continuously. We just need the right instruments to hear them. And if Ton 618 were suddenly transported to our galaxy, replacing Sagittarius A star at the center, the consequences would be catastrophic beyond measure. Sagittarius A star sits 26,000 light-years from Earth, anchoring the Milky Way. It weighs 4 million solar masses. We orbit it safely, feeling only the weakest gravitational influence. Now imagine TON 618 replacing it. 66 billion solar masses suddenly occupying the galactic center. The first effect would be gravitational. TON 618 weighs 16,500 times more than Sagittarius A star. The gravitational pull at the galactic center would increase by the same factor. Stars currently orbiting at safe distances would find their orbits destabilized. Stars near the galactic center orbit fast, some reaching speeds of thousands of kilometers per second. With TON 618 at the center, these velocities would increase. Some stars would gain enough speed to escape the galaxy entirely. Others would be pulled inward, crashing toward the center. The galactic disk would warp. The increased central mass would alter the rotation curve. Stars in the outer galaxy would feel a stronger pull. Their orbits would change. The spiral structure might dissolve or reform into a different pattern. Over millions of years, the galaxy would restructure itself around the new central mass. The process would be violent. Stellar collisions would increase. Gas clouds would collapse or be dispersed. Star formation rates would fluctuate wildly. But the immediate threat would come from radiation. If TON 618 arrived with its accretion disk intact, actively feeding, the quasar would dominate the sky. From Earth, 26,000 light-years away, the quasar would be the brightest object visible. It would outshine everything combined. The light would not just be bright, it would be deadly. X-rays and gamma rays from the accretion disk would flood the galaxy. These high-energy photons would strip away planetary atmospheres. The ozone layer on Earth would be destroyed in hours. Surface life would be exposed to lethal radiation doses. Even if TON 618 arrived dormant, without an accretion disk, the gravitational effects would doom life on Earth eventually. The altered galactic orbit would change Earth's position relative to the galactic center. We might drift into more dangerous regions, closer to the core, where stellar density and radiation levels are higher. The sphere of influence of TON 618 would extend across light years. Stars within several light years of the center would fall under direct control of the black hole. Sagittarius, a star's sphere of influence, is only a few light months. TON 618's would be hundreds of times larger. Thousands of stars would find themselves inside this zone. Their orbits would become chaotic. Close approaches to the black hole would be frequent. Tidal disruption events would light up the galactic center with X-ray flares every few years. The jets, if active, would be catastrophic. TON 618's jets stretch thousands of light-years. If pointed in the wrong direction, they could plow directly through populated regions of the galaxy. Any star system caught in a jet would be sterilized instantly. The high-energy particles would destroy everything. Fortunately, jets are narrow. Most of the galaxy would be safe from direct jet impact, but the jets would still affect the galactic environment. They would heat intergalactic gas, disrupt star formation across vast regions, and alter the chemical composition of the interstellar medium. The timescale of destruction depends on what state TON 618 arrives in. An active quasar would kill most life in the galaxy within years through radiation. A dormant black hole would take millions of years to disrupt the galactic structure through gravitational effects alone. Humanity would not survive either scenario. An active TON 618 would sterilize Earth immediately. A dormant one would eventually destabilize our orbit or place us in a more dangerous environment. Either way, the Milky Way, as we know it, would cease to exist. This thought experiment reveals how fortunate we are. Sagittarius A star is massive enough to hold the galaxy together, but not so massive or active that it threatens life. TON 618 is a monster. beautiful from afar but deadly up close. And the danger does not come only from its mass. The temperature gradient around Ton 618 spans extremes unimaginable anywhere else in the universe. Temperature near Ton 618 ranges from absolute zero to billions of degrees across relatively short distances. This gradient is one of the steepest in the universe. Move a few million miles closer or farther from the black hole, and temperature changes by factors of thousands. Far from the black hole, in the outer regions of the galaxy, space is cold. The cosmic microwave background radiation maintains a temperature of about 2.7 degrees above absolute zero. This is the baseline temperature of the universe, the leftover heat from the Big Bang. As you approach Ton 618, temperature begins to rise. The first source of heat is starlight. Stars near the galactic center are packed more densely than in outer regions. Their combined radiation warms the surrounding space to a few tens of degrees. Closer still, the accretion disk dominates. The outer edge of the disk, where matter orbits at slower speeds, might reach temperatures of thousands of degrees. This is hot enough to glow dull red like a cooling ember. Moving inward through the disk, friction increases. Particles collide more frequently. Orbital velocities rise. Temperature climbs. The middle regions of the disk reach hundreds of thousands of degrees. Matter here glows white-hot, emitting visible light and ultraviolet radiation. The inner edge of the disk, just outside the event horizon, reaches billions of degrees. At these temperatures, atoms break apart into plasma. Electrons strip away from nuclei. Matter becomes a soup of charged particles moving at relativistic speeds. This is hotter than the core of any star. Our star's core sits at 15 million degrees. The inner accretion disk of Ton 618 is hundreds of times hotter. The only places in the universe that reach similar temperatures are the moments after the Big Bang and the cores of supernovae. At billions of degrees, matter emits X-rays and gamma rays. These photons carry tremendous energy. Each one can ionize atoms, break chemical bonds, and damage biological tissue. The inner accretion disk is a death zone. Yet just beyond the accretion disk, temperature drops sharply. Space between the disk and distant stars is near vacuum. Without matter to hold heat, temperature plummets. A spacecraft passing just outside the accretion disk would freeze on one side, while the other side, facing the disk, would vaporize from radiation. This extreme gradient is unique to black hole environments. Stars have temperature gradients too, but they are gentler. The surface of our star is 6,000 degrees. The core is 15 million degrees. The transition happens smoothly over hundreds of thousands of kilometers. Ton 618's accretion disk transitions from billions of degrees to near vacuum cold over distances of a few million miles. The rate of change is thousands of times steeper. You go from plasma to frozen in the span of a few planetary diameters. The temperature gradient affects how matter behaves. Hot plasma in the inner disk has high pressure. This pressure pushes outward, opposing gravity. The balance between gravitational infall and radiation pressure determines how fast the black hole can feed. In the outer disk, temperature is lower, pressure is weaker, gravity dominates. Matter spirals inward more easily, but as it falls, it heats up, increasing pressure, slowing the infall. The system self-regulates. Temperature also affects the spectrum of light emitted. Hot regions emit short wavelength light, X-rays, and ultraviolet. Cooler regions emit longer wavelengths, visible and infrared. By measuring the spectrum, astronomers can map the temperature distribution across the accretion disk. For Ton 618, the spectrum peaks in the ultraviolet. This tells us the average temperature of the disk is around 100,000 degrees, but regions exist where temperature is much higher or lower. The spectrum is a weighted average. Understanding temperature gradients helps astronomers model accretion disks. The models predict luminosity, feeding rates, and spectral features. Comparing model predictions to observations tests our theories of how black holes grow. TON 618's temperature gradient is an extreme laboratory. The conditions near the event horizon cannot be replicated on Earth. Studying them from afar is the only way to understand physics at these extremes. And the heat is not the only extreme. The velocities near TON 618 approach fundamental limits. Matter near the event horizon of TON 618 moves at speeds approaching the cosmic speed limit. Orbital velocities reach 50% the speed of light. At these speeds, time dilation, length contraction, and relativistic effects dominate. The speed required to orbit a black hole depends on distance from the center. Farther out, gravity is weaker, and slower speeds suffice. Closer in, gravity intensifies, demanding faster velocities to maintain orbit. At the event horizon itself, even light speed is insufficient. Nothing can orbit at that boundary. Anything there must either fall in or escape outward. The innermost stable circular orbit, abbreviated ISCO, marks the closest distance where matter can orbit without falling in. Inside this radius, orbits become unstable. Any perturbation sends matter spiraling into the event horizon. For a non-rotating black hole, the ISCO sits at 3 times the event horizon radius. For TON 618, with an event horizon at 40 billion miles, the ISCO would be at 120 billion miles. At this distance, orbital velocity reaches about 43% of light speed. Rotating black holes have smaller ISCOs. The rotation drags space-time with it, allowing matter to orbit closer before becoming unstable. For a maximally rotating black hole, the ISCO can be half the radius of a non-rotating one. Matter can orbit even closer and reach even higher velocities. At 50% light speed, relativistic effects are significant. A clock moving at this velocity ticks 15% slower than a stationary clock. Distances in the direction of motion contract by 15%. Mass increases by 15% due to kinetic energy. For matter in the accretion disk, these effects are measurable. Spectral lines from hot gas near the event horizon show characteristic broadening and shifting due to relativistic Doppler effects. Gas on the side of the disk moving toward us appears blue-shifted. Gas moving away appears red-shifted. The velocities also affect collisions. When particles in the accretion disk collide at relativistic speeds, the energy released is enormous. These collisions heat the plasma to billions of degrees, producing the X-rays and gamma rays we detect from Earth. Matter, spiraling inward, accelerates continuously. As it moves from the outer disk toward the ISCO, orbital velocity increases. By the time it reaches the ISCO, it is moving at nearly half the speed of light. Then it plunges across the event horizon. The plunge happens fast. From the ISCO to the event horizon is a short distance, and gravity is pulling hard. Matter crosses the boundary in milliseconds, at least from the perspective of someone falling with it. From an outside observer's perspective, the crossing takes infinite time due to time dilation. During the plunge, matter continues to emit radiation, but the photons emitted become increasingly redshifted. By the time matter crosses the event horizon, the photons leaving it are stretched to infinite wavelength and carry zero energy. The matter effectively disappears from view. Orbital velocities near TON 618 are not just fast. They are among the fastest sustained motions in the universe. Only particles in cosmic rays or accelerated in jets reach higher speeds. And those are individual particles, not bulk matter. The kinetic energy in the orbiting matter is staggering. Each kilogram of material at the ISCO carries about 1/10 of its rest mass energy as kinetic energy. For reference, nuclear weapons convert less than 1% of mass to energy. The accretion disk is, in a sense, a far more efficient energy source. This is why black holes are so luminous. The conversion of gravitational potential energy into kinetic energy, and then into heat and radiation, is incredibly efficient. Up to 40% of infalling mass can convert to radiation before crossing the event horizon. Velocities this high also create stability challenges. The accretion disk is turbulent. Magnetic fields thread through the plasma, causing instabilities. Matter does not spiral smoothly. It clumps, creates vortices, and produces fluctuations in brightness. Yet despite the chaos, the disk maintains overall structure. Gravity and angular momentum conservation enforce order. The result is a dynamic equilibrium, a maelstrom held together by fundamental forces. And the velocities are not the only extreme property. The magnetic fields near TON 618 twist into configurations impossible to create anywhere else. Magnetic fields near TON 618 reach strengths millions of times greater than anything on Earth. These fields are not just strong, they are twisted, tangled, and shaped by the extreme rotation and gravity of the black hole into geometries that defy simple description. On Earth, the magnetic field is relatively weak, a few tenths of a Gauss at the surface. This is enough to deflect compass needles and protect us from solar wind, but not much more. In laboratories, scientists create fields of a few 100,000 Gauss with superconducting magnets. Near TON 618, magnetic field strengths reach billions of Gauss. These fields form naturally in the accretion disk. As charged particles orbit the black hole, they generate currents. Currents produce magnetic fields. The faster the particles move, the stronger the fields. The rotation of the accretion disk wraps the magnetic fields around the black hole like thread around a spool. Field lines that initially pointed radially get dragged in the direction of rotation. Over time, they wind tighter and tighter, spiraling around the black hole axis. This process creates a helical structure. Magnetic field lines form spirals that connect the inner disk to the outer regions. Plasma flowing along these field lines gets channeled into narrow streams. This is how jets form. The magnetic field acts like a guide rail, collimating the outflow. The fields also store energy. As they twist, magnetic tension builds. Eventually, the tension becomes too great. The field lines snap, releasing energy in violent bursts. These magnetic reconnection events are similar to solar flares but vastly more powerful. A single reconnection event near TON 618 could release more energy than our star produces in a million years. The energy accelerates particles to near light speed and generates flares of X-rays and gamma rays. The geometry of the magnetic field near the event horizon is particularly exotic. Frame dragging from the black hole's rotation twists spacetime itself. Magnetic field lines, threading through twisted spacetime, adopt bizarre shapes. They can loop, knot, and form structures that have no equivalent in flat spacetime. Some field lines might connect directly to the event horizon. These would appear from outside to spiral down toward the boundary and freeze there due to time dilation. The field lines would accumulate, creating an increasingly complex magnetic structure anchored to the horizon. The strength of the magnetic field near the event horizon is limited by the available energy. At some point, magnetic pressure becomes comparable to gravitational pressure. The field cannot grow stronger without disrupting the accretion flow. This balance sets an upper limit. For TON 618, the limit is extreme. Magnetic fields near the event horizon could reach tens of billions of Gauss. At these strengths, even light is affected. Photons passing through such fields can interact with virtual particles in the vacuum, subtly altering their polarization. The magnetic field also affects how matter falls into the black hole. Charged particles spiral along field lines rather than falling radially. This creates an asymmetric infall pattern. Some regions of the event horizon receive more matter than others. The accretion is lumpy and variable. Observing these magnetic fields directly is impossible. They are too distant and too small to resolve. But astronomers can infer their presence from polarization measurements. Light from the accretion disk becomes polarized as it passes through magnetic fields. The degree and direction of polarization reveal information about field strength and geometry. Radio observations are particularly useful. Synchrotron radiation from charged particles spiraling in magnetic fields is naturally polarized. By measuring polarization at different wavelengths, astronomers can map the magnetic field structure across the accretion disk. For TON 618, such measurements are difficult because of the distance, but studies of closer quasars reveal similar magnetic structures. Strong, twisted fields threading through the inner disk and launching jets. These observations support theoretical models. The magnetic fields near TON 618 are among the strongest and most complex in the universe. They challenge our understanding of plasma physics and magnetohydrodynamics. Replicating such conditions in laboratories is impossible. The only way to study them is through observation and simulation. And despite all this activity, despite the extreme feeding and energy output, TON 618 appears to have shut down. The quasar has stopped. The light we see from TON 618 left the object 10 billion years ago. We are observing the past, a snapshot of the black hole during an active quasar phase. But that phase may have ended billions of years ago. In the present day, wherever TON 618 exists now, it might be dark and dormant. Quasars do not shine forever. They require fuel. When the fuel runs out, the accretion disk dissipates. The jets shut down. The black hole goes dark. It still exists, still holds all its mass, but becomes invisible. A dormant monster waiting for the next meal. Several factors can shut down a quasar. The simplest is fuel exhaustion. Black holes eat the gas and stars around them. Eventually, the nearby reservoir is depleted. Everything within the sphere of influence gets consumed or ejected. The black hole starves. Feedback accelerates this process. As the quasar shines, it produces radiation and jets. These outputs heat surrounding gas and push it away. The radiation pressure from a bright quasar can exceed gravitational pull, blowing gas out of the galaxy entirely. The black hole destroys its own fuel supply. This self-regulation is why supermassive black holes and their host galaxies follow predictable relationships. Bigger galaxies have bigger black holes, but the ratio stays roughly constant. Feedback prevents runaway growth. When the black hole gets too large and too bright, it shuts itself down. Galaxy mergers can restart the process. When two galaxies collide, their gas clouds collide too. The collision disrupts the gas, removing angular momentum and causing it to fall toward the merged galactic center. The central black hole gets a fresh supply of fuel. The quasar reignites. TON 618 likely experienced multiple cycles, periods of activity followed by dormancy. Each major merger delivered fuel. The black hole grew in bursts. Between mergers, it faded and waited. Over cosmic time, mergers become less frequent. The universe expands. Galaxies separate. Encounters become rare. This is one reason why quasars were common in the early universe, but are rare today. Fuel delivery mechanisms have slowed. TON 618 may have experienced its last major merger billions of years ago. Since then, it has been coasting. The light we see today is the afterglow of that final feeding frenzy. By now, the accretion disk may have thinned and disappeared. Another possibility is that TON 618 is in a low activity state, but not entirely dormant. Small amounts of gas might still be trickling in, producing faint emissions we cannot detect from Earth. The black hole could be ticking along at a fraction of its peak luminosity. Observing the current state of TON 618 is impossible. Light from the present-day object will not reach Earth for another 10 billion years. We can only speculate based on what we know about quasar evolution. Studies of other quasars show that activity fluctuates on timescales of millions of years. A quasar can be bright for 10 million years, then fade for 100 million years, then reignite. The duty cycle, the fraction of time spent active, varies but is typically less than 10%. If TON 618 follows this pattern, it has spent most of its lifetime dormant. The active phase we observe is a brief flare in an otherwise dark existence. Dormant supermassive black holes are difficult to detect. Without an accretion disk, they emit no light. They are invisible. The only way to find them is by observing their gravitational effects on nearby stars. This works for nearby galaxies, but not for objects 10 billion light-years away. This means the universe could be full of massive black holes we cannot see. TON 618 might not be unique. There could be others, even more massive, lurking in distant galaxies. We only see the ones that happen to be feeding when their light reaches us. The shutdown of TON 618 also marked the end of its role in shaping the universe. Active quasars regulate galaxy formation and enrich the intergalactic medium. Dormant black holes do neither. They sit quietly, relics of a more violent past. But even in its dormant state, TON 618 is not the most massive black hole. There are others, rare and distant, that push the limits even further. TON 618 is extreme, but it is not alone. Other supermassive black holes rival or exceed its mass. These objects, scattered across the universe, represent the upper end of the black hole mass spectrum. Phoenix A holds the current record for the most massive black hole by some estimates. It sits at the center of the galaxy cluster Abell 2744, roughly 5.7 billion light-years away. The black hole weighs approximately 100 billion solar masses. That is more than 1.5 times the mass of TON 618. Phoenix A is also surrounded by one of the most powerful radio sources ever detected. The jets extend for millions of light-years, carving enormous cavities in the surrounding intergalactic gas. The energy required to excavate these cavities is almost incomprehensible. But Phoenix A's mass estimate comes with uncertainty. Different measurement methods yield different results. Some analyses suggest it might be lighter, closer to 50 billion solar masses. Others confirm the 100 billion figure. The distance and obscuration make precise measurements difficult. Holmberg 15A is another contender. This black hole sits at the center of the supergiant elliptical galaxy Holmberg 15A, roughly 700 million light-years away. Mass estimates range from 40 billion to 170 billion solar masses, depending on the method used. Holmberg 15 are formed through multiple galaxy mergers. The black hole consumed several smaller supermassive black holes over billions of years, growing to its current size. The surrounding galaxy shows signs of this violent history. The core is unusually large and depleted of stars. S50014 plus 81 is a quasar even more distant than TON 618, at 12 billion light-years. The black hole weighs about 40 billion solar masses. Like TON 618, it existed when the universe was young, presenting the same formation timeline problems. How did it grow so large so quickly? SDSS J100 plus 2802 is another early universe quasar, at 12.8 billion light-years. The black hole weighs 12 billion solar masses. It appeared when the universe was less than 1 billion years old, making it one of the earliest known supermassive black holes. These early massive black holes challenge cosmology. They appeared too soon. There had not been enough time for them to grow through standard accretion. Every one of them requires exotic formation scenarios or super Eddington feeding rates. Sagittarius A star, our home galaxy's central black hole, weighs only 4 million solar masses. Compared to these giants, it is microscopic. Yet it anchors a galaxy of 200 billion stars. The relationship between black hole mass and galaxy mass varies widely. Some small galaxies have surprisingly massive black holes. Others, massive galaxies, have relatively small black holes. The correlation is loose. Environment, formation history, and merger activity all play roles. NGC 1277 contains a black hole weighing 17 billion solar masses in a galaxy much smaller than the Milky Way. The black hole represents 14% of the galaxy's total stellar mass. For comparison, Sagittarius A star is less than 0.1% of the Milky Way's stellar mass. NGC 1277's black hole is absurdly large for its galaxy. Theoretical limits suggest black holes cannot grow arbitrarily large. Feedback mechanisms shut down growth. Fuel supplies run out. The universe's expansion separates galaxies, reducing merger rates. Somewhere, there is a maximum mass. Current estimates place the limit around 100 billion solar masses, possibly higher under perfect conditions. Phoenix A may be approaching this limit. If so, it represents the largest black holes that can form in our universe. But measurements remain uncertain. Many of these extreme black holes sit at immense distances. Observational challenges make precise mass determination difficult. Error bars are large. The true ranking of most massive black holes may shift as better data arrives. What is clear is that the universe produced multiple monsters. TON 618 is extraordinary but not unique. Supermassive black holes weighing tens or hundreds of billions of solar masses exist in multiple locations. Each one is a cosmic marvel. These black holes also serve as laboratories. Their extreme gravity tests general relativity. Their formation history constrains models of galaxy evolution. Their influence on surrounding matter reveals how structure forms in the universe. And their power extends beyond gravity. Even neutron stars, the densest objects besides black holes, would not survive an encounter with TON 618. Neutron stars are the densest objects in the universe besides black holes. A neutron star weighs about 1 to 2 times the mass of our star, but compresses that mass into a sphere 20 kilometers across. 1 teaspoon of neutron star material would weigh 1 billion tons on Earth. The matter is so dense that protons and electrons have merged into neutrons. The entire star is effectively a single atomic nucleus, held together by neutron degeneracy pressure. This pressure is what prevents the star from collapsing further into a black hole. Neutron stars are tough. They survive supernova explosions that destroy normal stars. Their surfaces are solid, harder than diamond but made of exotic nuclear matter. Their magnetic fields reach trillions of Gauss. They seem indestructible. But against TON 618, even a neutron star is fragile. If a neutron star wandered too close to the black hole, tidal forces would tear it apart. The process would be violent and brief. As the neutron star approached, the near side would feel stronger gravity than the far side. This creates a tidal force, stretching the object. For most objects, this stretching begins gently and intensifies gradually. But neutron stars resist deformation. Their internal pressure is enormous. The star holds its shape stubbornly. Tidal forces must overcome degeneracy pressure before the star deforms noticeably. Close to TON 618, tidal forces would eventually win. The gravitational gradient would exceed the star's structural strength. The neutron star would begin to elongate, stretched into an ellipsoid. The stretching would accelerate. As the star deforms, the tidal forces increase on the extended regions. Positive feedback loops in. The elongation accelerates. Within seconds, the neutron star would resemble a cigar rather than a sphere. Then disintegration. The tidal forces would overcome neutron degeneracy pressure entirely. The star would rip apart, fragmenting into streams of neutron-rich matter. These streams would spiral toward the black hole, heating as they compressed in the accretion disk. The disruption would release enormous energy. A neutron star carries gravitational binding energy equivalent to about 10% of its rest mass. When torn apart, some of this energy converts to kinetic energy and radiation. The result is a brilliant flare visible across the galaxy. We have observed similar events involving normal stars. Tidal disruption events happen when stars wander too close to supermassive black holes. Telescopes detect sudden X-ray and optical flares as the stars get shredded. These flares fade over weeks or months as the disrupted material settles into the accretion disk. A neutron star disruption would be more energetic. The star is more compact and carries more binding energy. The flare would be brighter and richer in high-energy photons. X-rays and gamma rays would dominate the spectrum. The disrupted material would behave differently than normal stellar matter. Neutrons are unstable outside nuclear environments. Free neutrons decay into protons, electrons, and neutrinos within minutes. The stream of neutron-rich matter spiraling into Ton 618 would rapidly convert into ordinary matter, releasing additional energy in the process. Some of the material might not fall into the black hole immediately. Part of the disrupted neutron star could be flung outward at high velocity, escaping the system entirely. This ejected matter would seed the surrounding space with heavy elements, including rare isotopes produced in the extreme conditions of the disruption. The frequency of such events is unknown. Neutron stars are rare, and most orbit safely in binary systems or drift through empty space. The chance of one wandering close to a supermassive black hole is low. But in the crowded environment near Ton 618, where stellar density is high, such encounters are possible. Each disruption would add 1 to 2 solar masses to the black hole, not much compared to Ton 618's total mass of 66 billion solar masses. But over millions of years, if disruptions happen regularly, they contribute to growth. Neutron star disruptions also produce gravitational waves. The final moments before breakup involve a compact object spiraling in a strong gravitational field, accelerating rapidly. The space-time distortion generates waves detectable by future instruments like LISA. Observing such an event would be a treasure trove for physics. It would probe matter at nuclear densities, test general relativity in extreme fields, and reveal how tidal forces operate near massive black holes. Ton 618, with its immense gravity and sphere of influence, would be the ultimate laboratory for such studies.